So if we could all mute ourselves, I'll do the same. And over to you, Nick, for 40 meters on a glue stick.
Thank you very much. Now, do you have to spotlight me or something? So, or perhaps you already have, but so I'm big
No,
because I'm going
we
to be
all do that
showing a
ourselves.
presentation.
We all do that ourselves, to be honest. Um,
Okay.
but you can share now. So if you can try sharing, we'll see what
Okay.
happens.
Yeah. All right. Yeah. Sound. Video share. It won't let me optimize the video, but it'll let me share the sound. Okay. Well, that should be fine.
Yeah, that's perfect, Nick.
Okay, is that all right? Let's just get this going. Right. Fine. So hopefully that will be nice and big on your screens. Yeah,
Certainly
brilliant.
is. Yeah.
Brilliant. Well, thank you very much, Simon, for the welcome and indeed for the invitation. Again, I can't believe it. I think it was like 3 years ago when I came and spoke to you. So quite a long time ago. And I have a sneaking suspicion that I spoke about building a direct conversion then, but I built a few in the meantime. This is one with a difference, and you'll see why that is. Now I'm aware I'm speaking to the AM Society here about single sideband yet again, but yeah, it's another kind of construction project. This one was a little bit more challenging. Because I was not going all high tech. In fact, I was going in the opposite direction. But I'll say a bit more about that in a minute. So, and apologies if you've got a very good memory and you can remember some of the things I said last time. But I'm just going to go over a little bit of ground just because I think it's worth repeating. So, it's my contention really that you can essentially build all analog radios out of 4 different building blocks. Now, these are wide generic terms, and there are lots of different flavors of these building blocks, if you like. But essentially, you can strip it down to just 4, and those 4 are filters, mixers, oscillators, and amplifiers. And pretty much all analog radios are just different combinations of different kinds of these basic 4 blocks. So if you're somebody like me that builds in modules, that's really helpful because you can pick a block and do it. Now, obviously you get different types of filters. There's different types of mixers, but humour me. Now, there is a radio which is just about the simplest radio that you could listen to single sideband on, which uses just one of each of these types, and that is a direct conversion receiver. Because when you really strip it down to its basics, essentially what you have is your antenna going into your bandpass filter, and the one I'm going to be showing you was for 40 meters, and that's what this direct conversion receiver was built for. And then you pass the signal from the bandpass filter into the product detector, which is just a mixer. It's just a mixer that mixes down to baseband, to audio. And a mixer has 3 ports. It has 2 inputs and 1 output. So one of your inputs, of course, is your 40 meter RF signal. The other input is coming from your local oscillator. And those mix together, and we will recover just one of the outputs from the product detector, which will be the audio signal, and that will go to our audio amplifier and then out to our loudspeaker. So it's about as simple as it gets, really, when you're thinking about single sideband. Now I can't see everybody's screen here, so I wouldn't know, but it's interesting to ask the question. I wonder how many of you have, and I'm aware I'm talking to the AM Society here, but how many of you have listened to single sideband on a direct conversion receiver before? Because if you haven't, you're in for a bit of a shock because it sounds it can sound messy, right? And it can sound, because as you can see from this block schematic here, the only filtering is the bandpass filter. The only other filtering is what's in between your ears, right? You know, so you've got no nice narrow filtering and cancelling out the opposite sideband or any of that stuff. So there's a lot of stuff going on, and it can sound a bit messy, particularly if you're used to, you know, all the newfangled software-defined radios with their brick wall filters and stuff. It can be a bit of a shock to the system for some people. But to be honest, I love direct conversion receivers because it's so simple. You know, you're not messing around with the signal at all, really. You're taking the signal and mixing it straight down to audio, so it can sound wonderful and really good, mainly because you're not constricting it to 2.3, 2.4, 2.7 kilohertz of audio. You know, it's as big as you know, the sound frequencies your ears can hear. So it's pretty good. How does it work? Okay, now, hand on heart, this is the only slide where we're going to get into some serious RF theory here. To be honest with you, I love this stuff. This is why I build. I build so I can understand this stuff, and I live for this stuff. But not everybody, you know, some people have a life. So if this doesn't float your boat, then just, you have my permission to zone out for the next couple of minutes. But if you are interested in how a direct conversion receiver works, here's how it works. So here's our product detector, our mixer. Imagine that we've got a signal, a single sideband, lower sideband signal that we're receiving. And just to keep the maths simple, let's imagine it's 3 kilohertz wide. I know that in all reality, it's probably not going to be 3 kilohertz wide, but it just makes it a bit simpler. So imagine that we've got a lower sideband signal sat between 7097 and 7100 kilohertz. We're going to mix that with the signal from our local oscillator. Now we're going to set our local oscillator at 7100 kilohertz. So that will give us, well, actually, it will give us a whole bunch of different stuff, actually. But the two main products from that we're interested in are the sum frequency, first of all. So this is where we take the RF and add it to the LO. And as you'll see there, we end up with a signal, well, in the middle of the 20 meter band, 14197 to 14200. That's not going to bother us because we're going to filter that out, right? What we're interested in is the difference. So that's the RF minus the LO. And when you're calculating this, I mean, at the end of the day, mixers are not that clever. They don't know whether they're supposed to be minusing the RF from the LO or the LO from the RF. But for our point of view, personally, I think it's much more helpful if you always start with the RF. You'll see why in a minute. So RF plus LO, RF minus LO. So RF minus LO, 7100 minus 7100 is 0, right? Well, that's what we want, mixing down to baseband. But look at this. 7097 minus 7100 is minus 3 kilohertz. We said, just a minute. How can you have minus 3 kilohertz? Well, you can't. Well, you can mathematically. That's exactly what it is. But in reality, of course, there's no such thing as minus 3 kilohertz. There's just 3 kilohertz. But that minus tells us something really important, right? And that's, we'll get to that in a minute. Now, let me just illustrate this. A picture paints 1,000 words, as they say. So let me show you a little diagram like this. Okay, so as you can see, so this is our 40 meter signal that we're trying to receive. And there is our lower sideband signal sat there between 7097 and 7100. Now, what I want you to imagine is on the vertical axis, the y-axis, that's not amplitude. It's the frequency of the modulated audio signal. Let me say that again. So in other words, the higher that bit of green, the higher the frequency of the audio signal, the modulated audio signal. So in other words, when you look at that, you'll see the highest audio frequencies are on the left and the lowest audio frequencies are on the right. So that instantly tells you something about lower sideband. It's inverted, right? Because as we tune up from 7097 to 7100, we're tuning up. We're going up in frequency, RF frequency, but we're going down in the frequency of the modulated audio, right? So it's inverted. It's back to front. That's not a problem, because we're going to invert it in a minute ourselves, right? But it's just to make the point that, and of course, if we had the lower sideband from 7100 to 7103, it would be the opposite. It would not be inverted. Okay, so there's our signal. So what happens then when we mix in our local oscillator at 7100? Well, mathematically, we get this, right? We get a signal lying between -3 and 0, but of course it doesn't exist. But what that minus tells us is that the signal is inverted. So what actually happens is this. Watch closely. 3, 2, 1. It goes whoa, 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 and it folds around the DC point. So now look at this, right? So now we've got our signal. It's now our audio signal, but it's the right way round, right? Line between 0 and 3 kilohertz. Happy days, you say. We've got the right signal, the right way around. What could possibly be wrong with the world? Well, not so fast. Because the problem is, unfortunately for us, 7097 to 7100 kilohertz are not the only range of frequencies that when mixed with 7100 will give you that particular frequency. So let's imagine, for instance, if we had an upper sideband signal shown in yellow there. Now, if we had an upper sideband signal in that particular position, what would happen is that would mix down, and because it's upper sideband, there's no spectral inversion, so it would mix down like that, right over the top of our lower sideband signal that we want to listen to. But, I hear you say, who's going to be operating upper sideband in the middle of the 40 meter band? Well, probably nobody. But what you very well may find, particularly if the bands are busy, if it's a weekend, if there's a contest on, you probably will find 3 kilohertz above your signal, another lower sideband signal. And because it's in what is effectively the upper sideband slot for our signal that we want, there's no inversion, right? Because and that will mix down exactly as it is over the top of our signal. So that's why what we actually listen to when we're listening to single sideband on a direct conversion receiver is we're listening to the signal that we want to listen to, and we're also listening to an inverted form of what's lying 3 kilohertz above us. So it sounds like you're trying to listen to your signal and some idiot's working upper sideband over the top of you. That's what it sounds like. And that's why it can be so messy. And when you first start tuning around with a direct conversion receiver, it's like sensory overload sometimes because there's so much stuff going on. But actually, when the signals are spread out a bit more, it can sound wonderful. And you will hear it in action a little bit later on. So anyway, that's how it works. There's unfortunately nothing you can do about this unless you change the architecture of your radio, which you could do. You could get another mixer. You could have a quadrature LO, and you could do a phasing system where you cancel out the opposite sideband, or you could convert it into a super heterodyne, in which case instead of just mixing it down to baseband, you mix it down to an intermediate frequency, then you put it through a real narrow crystal filter, so narrow that only the bit we want gets through. So when it comes to mixing it down to audio, we ain't going to worry what's 3 kilohertz above it because we've already filtered that stuff out, right? So that's the only thing you can do with that. Anyway, let's crack on. So I challenged myself at the beginning of last year to build another direct conversion receiver, but this one I set myself 2 huge challenges. Firstly, I was only going to use analog modules, and secondly, I was only going to use discrete components. So only analog modules. That means Arduinos, SI5351 phase lock loop generator modules, none of it, right? it's all got to be analog. And also all discrete components. So no ICs, right? No NE602 mixers, no LM386s, none of it. It's all going to be individual transistors, right? So this was my kind of retro challenge, if you like, having played around with all the techno stuff to see whether I could do this and what this would be like. Right, okay. So I'm going to show you those 4 different modules, and we're going to spend more time on some than others, and because some of them are a bit more interesting, I think, than others. So quickly, so first of all is the bandpass filter. Now I'm not going to show you schematics and stuff for this. If you're interested in this, I've got a ton of videos on my channel about every conceivable flavour of LC filters. So if you want to have a look at that, then please do. This is a classic double tuned circuit built to the specifications of Hans Summers from QRP Labs. And I bought, when I first started this, before I was brave enough to build scratch build a filter myself, I bought a kit from Hans Summers, and you can download the instructions off his website. And his instructions are absolutely brilliant. They're really, really clear and excellent. So I'm afraid he only ever got the price of one filter from me, because after that I've built all my own according to his instructions, because his instructions are so good. The thing with a bandpass filter, with a low pass filter, that's a simpler thing. You can put a bunch of just, you know, you've got to calculate it, of course, but you get the right amount of inductance, the right amount of capacitance, stick it in, you got a, you know, fair to middling chance that it's going to work okay. With a bandpass filters, I've got a video called The Dark Art of the Bandpass Filter, because it frightens a lot of people because they are far more fiddly to do. So you'll see, I'm not sure if you'll see my, can you see my cursor if I wave my cursor around here? You might not be able to see it.
Yeah, we can see it.
It's a little black thing here. Yeah, I should have made it bigger. But so it's essentially two tank circuits, really. So you've got these are actually transformers. So the primary is an inductor, and then the secondary is just a few little windings. Does a bit of impedance matching for 50 ohms for the input and output. So you've got an inductor there with this capacitor. So here's a fixed capacitor. This is a fixed capacitor. These just go into ground. So you've got 2 in series, and then you've got another one here in parallel. And exactly the same on the other side. These are mirror images of each other. And so you've got some variability in the capacitance. You've got some variability in the inductance, but it means squishing the turns together, spreading them out, adding turns, taking them off. So that's a bit more faffy. And then this little cheaper trimmer in the middle, this is a really important one, because this is the coupling capacitor, and a lot of people get this wrong. It's usually a tiny amount, maybe just less than 10 picofarads. It could be as little as like 3 or 4, which is why this is a very low value one. And essentially what happens is these 2 tank circuits you tune, and you adjust these capacitors, and you might have to adjust the inductors, so that you get the right, well, your filter is sat in the right place. So by adjusting these, you can move up or down in frequency, the whole filter. And actually the coupling capacity links the 2, and this is how you get a decent shape, because, you know, if it's overcoupled, you'll get the twin peaks, and if it's undercoupled, you'll just get one peak, and you want the kind of classic filter shape where it's flat on top and curving down, you know. So, and they take a bit of getting used to doing, but once you've done a few, you'll be doing them in your sleep, really. But they're quite cool little things. So anyway, so that's, if you're interested in that, by all means, check out the QRP Labs website and have a look at my YouTube site if you want some information on how to build them yourself. So that's the the bandpass filter. Now, the product detector. I decided when I did a few different variations of this. So for the product detector, I thought I'd have a go, first of all, at doing an active one. So this is a design that comes from the living legend that is Mr. Pete Giuliano, N6QW of Solder Smoke fame. And he built a circuit that was originally designed for a dual gate MOSFET, which are pretty much unobtainium these days. So he used two J310 JFETs together as it were as one dual gate MOSFET. So you'll see down here there's a transformer here, impedance matching transformer here. So the RF comes in on the gate of the bottom transistor. The VFO comes in on the gate of the top transistor, and then you take the IF, or the audio in our case, off the drain of this top JFET here. This is a little audio filter that filters out any RF. So we just have the audio frequencies, and then we take that out. Now, I think I've got a picture of it here. Yeah, there it is. And so I built this, and it worked really well. I've run the whole radio on 9 volts, so it doesn't need any more than that. The problem is, in a way, it worked a bit too well. Now, there's an interesting irony here as I'm talking to the AM Society, but I had a problem with broadcast AM breakthrough. And, you know, certainly living in the UK, as we know, we're in quite close proximity, so some pretty strong broadcast AM stations over in Europe and beyond, many of which lie just north of our 40-meter band. And it's it's too close to filter them out with a bandpass filter, really, unless you're going to be very, very clever with it. So it's quite tricky. And my particular nemesis was Radio China International, which I think is just north of the top end of the 40-meter band. Well, I was hearing Radio China International all through the 40-meter band, accompanied by CW, accompanied by single sideband. You know what? Because it's such a strong signal, it was coming through. And actually, when I did some work on this, it seems that for as long as people were putting dual gate MOSFETs into product detectors, people were moaning about broadcast AM breakthrough. And I think it's just an inherent weakness, I'm afraid, of the design. And I've yet to find a way to actually do anything about that. So it works really well. But depending where you are in the world and depending what time of day you're using it, but if you're trying to use it in the evening when all the broadcast stations are, are cranked up fully, then that could be tricky. So I thought, well, yeah, it works, but I think I could do better. So I think I need to try again. So I went back to my tried and trusted diode ring mixer, double balanced diode ring mixer, which I've made many of in the past, and they all work well. And I tried this, don't worry about any of this circuitry down the bottom for a minute, just ignore all that for a moment. So I did the kind of vanilla mixer. It worked well, it was really good, but I was still getting a little bit of this AM breakthrough. Not a lot, it was a lot better, but there's still... Now, part of that is because obviously this is a passive thing, 6 dB of loss in it as opposed to any gain. And so I contacted Bill Mara, also from Solder Scope fame. We correspond on various things from time to time, because I knew he'd had a similar problem. His was Radio Marti, which was a strong AM station in the Caribbean that he was picking up in the States. And he said, have you tried, Nick, Roy Llewellyn's audio diplexer? Now, Roy Llewellyn, you may have heard of Roy Llewellyn, famous for antenna modelling software that many of us use, W7EL, but he also created this little circuit. It's very few components. Now, it's this here, if you can see it, hanging off the IF port. So it's a 100 nanofarad cap and then a 51 ohm resistor to ground. So whatever happens, it's the IF port is going to see a good 50 ohms match. That's really, really critical. Then it's going through a 100 microhenry choke. choke off any of the RF, and then there's some of the capacitors here which act as a filter. Ignore the switching. It's because I ended up putting this into a transceiver, so I've got some kind of receive and transmit switching going on here, which obviously I didn't need in the direct conversion receiver. So I built it and put this little thing in as well, and I think I've got a photo of that. Yes, so the filter bit is his audio diplexer is just this bit coming out here, just these few components here. It's tiny, really. And how well did that work? Well, I want to show you some results of some measurements that I took. So what you're seeing here is what I decided to do was I figured if I could kind of use the mixer, because mix-up modulator, it just depends whether you're taking a signal out or putting a signal in, right? It works the same way. So if I could use it as a modulator and judge what the carrier suppression is like, and that's probably heresy to you AMers, isn't it? You know, carrier suppression, but but forgive me. But if I could judge what the carrier suppression was like, then actually I've got a good indication of how it's going to work the opposite way round then on receive. So that's what I did. So what you're looking at here is a screen grab from my spectrum analyzer, and all I did is I took this is the vanilla homebrew diode ring mixer, not with the Roy Llewellyn diplexer, just the basic, you know, transformers and the diodes. And I fed that a signal, or both signals from my signal generator. And you can see here, so here's the two side bands, and here's the carrier in the middle, and that's all right. I mean, what do we got? 10, 20, 30 odd dB of carrier suppression. All right, but I thought, well, could do better. Now, you might be thinking, well, Nick, it's because, you know, it's your homebrew mixer, isn't it? You know, if you spent some money and bought a commercial one, then, you know, it might work better. What, you mean like this? Let me show you that again. So that's mine, right? This next one, I won't mention who it's manufactured by, is a commercially available double balanced diode ring mixer. It's about 7 dB worse than the one I built, right? So clearly it's not the design of the mixer. But get a load of this, right? When I took my own homebrew double balanced diode ring mixer and I put those 4 components of Roy Llewellyn's audio diplexer on it, this is what I got. You ready for this? Look at that. I mean, what carrier? What carrier? I mean, it really gets no better than that. And that, gentlemen, is the difference that a solid 50 ohms impedance on that IF port makes. Incredible, absolutely incredible. So I was more than pleased with that. So I thought, right, that's definitely staying in the radio, right? So we got the filter, we got a product detector that works really well. What's next? Well, next I thought I'd have a go at the audio amplifier. Now this was always going to be a bit of a challenge for me because, you know, I mean, I'd used lots of discrete components in lots of stages before, but I've got to be honest, I'd never built an audio amplifier with all discrete components before. I'd used, you know, TDA 2003s and LM380s and all kinds of stuff before. So this was a design that was published in Sprat 129, which is the I'm sure many of you know the magazine of the GQRP club, which I'm a member of. And this was by Dieter Gens OW8DIZ. And essentially what this is, it's a kind of a pair of transistors, two N3904 and two N3906. So the NPN and the PNP in a kind of Darlington configuration here as a kind of preamp. And then he's got the same pair, the 3904 and the 3906, in a kind of push-pull AB class amplifier as the kind of power stage, right? And it works really well. And I think I've got a picture of it here. yeah, so that was the one I built. Ignore that transformer. That was an experiment from something else. So that's not actually in circuit. I could have dusted it as well by the looks of it, but no, sorry about that. But so, and it works great, absolutely fine. But when I published the results of this, Pete Giuliano, N6QW, got in touch with me and says, Nick, he says that's great. He says, but have you tried swapping out those last two NPN and PNP transistors for some audio power transistors, the TIP 31C and the TIP 32C. So this is Pete's design, which is very similar to the other one. You know, he's got he's got the two. He's actually got two NPNs as a driver, and then he's got the similar thing here. He says, don't change the biasing or anything. Just rip out the small ones and stick these bad boys in and see what difference it makes. And sure enough, it was absolutely brilliant. So it worked just as well, and it had a lot more power, and draws obviously a bit more current because it's producing more power, but pretty good. And so I think, yeah, and that was that one. So yeah, so I didn't rip them out. I just built another one because they're, you know, small little things. The great thing with audio, building for audio, of course, is that you can use strip board. Obviously, you wouldn't want to do that with RF because of all the stray capacitance. But for audio, it's great. And for me, it means I can build things small, which is a novel experience for me because most of my stuff's huge. So, yeah, so that was that. So I thought, that's great. That's a keeper. We'll go with that. And so that, I think, leads us on to the last stage, which is the oscillator. And this is the most exciting thing about it, and this is really the whole title of the presentation. And this was the whole thing that kicked this project off. And where it starts, it actually starts with Asher Farhan, VU2ESE of the BitX fame. And Farhan just posted, I didn't announce it, he just posted at some point on his website 2 new designs for transceivers that he built and he was inviting us to build. One of them was for the S-BitX, which is this kind of software-defined version of the micro BitX. And the other one was for something he called his Daylight Again transceiver. And you couldn't have had 2 more different circuits if you tried, because the S-BitX is the highfalutin SDR, and the Daylight Again is all analog, all discrete components. Now, I say all discrete components. He has got some voltage regulators in there. Technically, I think they constitute ICs, but we'll let him off that. And you'll have to forgive me as well, because I used his design and stuck a voltage regulator in. But apart from that, they are. So he basically, so this is his little oscillator. It's 2 J310 JFETs, but it is a PTO. It's a permeability tuned oscillator. So what that means is, unlike your kind of classic VFO where you'd have a fixed inductance and then you'd have a thundering big variable capacitor that you would tune, with a permeability tuned oscillator, you have a fixed capacitance and you vary the inductance, which actually is a bit more tricky to do physically, logistically, if you think about it. And I mean, it's not a new thing. I mean, if you think of the old AM car radios, actually, when you used to kind of press them in, I mean, that was based on a PTO kind of idea. Now, what Farhan did is he 3D printed a little plastic former that was basically like a little former freeze winding, so you could wind your induction coil on it, and it had a space so he could screw this brass screw in and out of the former with the windings on. Now, as the purists were quick to point out to him, technically this is not a permeability tuned oscillator, because brass has the same permeability as air. So it's not. So he's not changing the permeability, but it is a variable inductor, and it worked very well. The only thing was, of course, is when you tuned, the whole tuning knob, as it were, either went in or came out towards you, because that's how he constructed it. Now, I knew about this. I'd seen it. I thought, that's interesting. Maybe I'll get round to that one day. The game changer for me was, again, name dropping Bill Mara, who put something up on Solder Bespoke about. He said, "Oh, someone's contacted me," and he says, "I remember someone had contacted him ages ago about they'd made a permeability tuned oscillator, and they'd used a glue stick." And they said, put this glue stick in, and Bill had to go at doing it. And he says, it is amazingly stable. This circuit is incredibly stable, way more stable than most kind of variable cap tuned VFOs are. Well, I was hooked on this. I thought, no way, a glue stick, right? So I was in the middle of a project. I just put it all down. I put it all down, and I bought a box of glue sticks, right? So here they are. Now, I'm sure you're familiar with the idea of how a glue stick works. It's a bit like a lipstick or anything. So essentially, there's a little kind of threaded shaft, and the knob on one end, and there's a little kind of plate that sits on the shaft. And as you twist the knob, it works this little plate up and down this threaded shaft. So what I did was this. Now, I've actually got one of these here, which you won't be able to see. Well, at the end of it, I can show you some of this stuff, because it'll be a lot bigger. But so it's this kind of idea. So you kind of thread it on. You can see I've got some cable ties on there to hold the thing. You tap it off there, not far in, on one about 3/4 of the way through, I suppose, as well. You need that. And then what you do, so this is the inside. So basically, that little kind of grey thing you can see, that's the little shaft, that's the little seat that moves up and down the shaft. And the shaft you can just see is a little green dot inside there, and that's the top of it. And what I did is I glued, they are T50-6s, those yellow cores, two of those, one on top of each other, and inside that little plate. I had to get the Stanley knife and just shave a bit of the plastic round, just so I could accommodate them. They fit in, and crucially, they will accommodate the shaft, because the shaft goes through the middle of the toroids then. And then by actually doing that, I won't bother showing that, I'll show you at the end. But when you turn it, so as the shaft moves forward, so these iron dust toroids are moving through the coil, right? So this is a true permeability tuned oscillator, because you're changing the permeability of the whole thing as you're actually doing this. And yeah, I tested it. That was twice as much. I had to take some of the turnings off here. So now, this is what I've got. I'll show you this here. This is not a proper schematic, but I often produce these things, particularly when I'm building Manhattan style. So I thought it was worth just showing you, because this is what I do. So this is this is more about where I'm going to lay the things out as much as anything else, because it's all very well having a schematic, but very often schematics, they don't look like the actual component or represent how big the components are or anything when you're trying to actually lay it out in a certain space. So you can see I've got the former down here. So in the end, I only needed 3.46 to 3.80 microhenries. And that would allow me to tune from 6.97 to 7.26 megahertz. So, I mean, ideal, right? And so into the right the way through the 40 meter band. And that's with a fixed capacitance of 135 picofarads. So, which is great, because you can just get some NP0, C0G capacitors, the real good thermally stable ones, and make up that figure, and you ain't going to worry about it then. Don't worry about this, but this is when I originally did it. The first one I did, I just used some random toroids I had just to see whether the thing worked. And when it worked, then I decided to build it a bit more carefully, and so I built another one. So that was that. And yeah, that's what it looks like in the tin. So you can see I basically just made a hole and stuck it out in the tin. That's actually the second one. The first one I built, I don't know whether you can see here really, but was on here. So actually all the gubbins is actually inside that tin there, but the coil I've put on the outside. Now, no prizes for guessing the problems that I had with this. 2 words: hand capacitance. Because if you look, all those turnings, and I use thundering big antenna wire as well. As I'm putting my hand over to turn, my fingers are so close. I got like a Theravin or what you call it. So, every time you go near it, because it was too close. You know, my hand was too close to it. So that's why I ended up going for this thing and actually enclosing the thing in a tin. And grounding it as best as I can. As you can see in the photo there on the slide, the nut at the end that is grounded. So I mean, you can't really ground this because it's plastic. But to do my best to try and negate the kind of hand capacitance. So I built the Firehand design, or pretty much adapted the Firehand design on the little copper-clad board, and then hooked it up to this, right? And was amazing at how well it did. Now, okay. Oh yes, I made a video about it on YouTube. Suddenly, the views started going through the roof. Thousands of that. I thought, I don't normally get this many people watching me. What's going on? And I hadn't realised till somebody told me that Jenny List from Hackaday had picked it up and had run a story on it. So everybody was going and watching this video. Which was marvellous. And but yeah, so I think we're nearly there. You'll be pleased to know. What I've got to show you now is some video footage now when I put all this stuff together. So you're going to hear the direct conversion receiver with the glue stick PTO, and then at the end I couldn't help myself. I had to kind of put this in, but you won't believe this. I had to run a little experiment. So just watch to the end because you'll be amazed at what this little thing can do.
Yeah, am I supposed to be getting some audio, Nick? I can't hear anything.
Yeah, lovely. Thank you, Kelvin. MW7KDA from
you're not hearing any audio?
PPY. Yes, you're picking about 5 and 7, Kelvin. About 5 and 7.
I've got audio.
But there is quite a lot of fading on the band.
You might need to turn it off a bit, your
Thank you very
volume.
much indeed for the nice support. It's quite an old station here, but we've got a fairly decent microphone on it, and I'm cheating a little bit. I've got a little bit of compression on as well, and we can adjust the equalisation on that as well, so hopefully it's matching my voice okay. We're currently running about 450 watts out from the linear. George X-ray calling. M0RBI, Mexico 0, Radio Bravo Italy. M0RBI, G4B, GX calling.
Okay, so this was a bit of an experiment, but I just had to try it really. So I've got almost the same setup as you saw before. So got the PTO connected, drawing about 30 milliamps as usual, except that I've disconnected the speaker here, and you'll see I've got another audio cable connected into that audio output, and that, if I just follow it, ignoring all the graveyard of other projects going on here, going over here, and it comes into finally into this, and this is a little Behringer external audio interface, and that it connects via USB to my Mac, and get a load of this. Yeah, I'm decoding FT8 on a glue stick PTO. Unbelievable. And I'm going to do a screen capture now, so you'll see this in more detail, but I just had to try it, but absolutely amazing. So you can see on my Mac I'm running WSJTX, and I've also got a browser running down the bottom left, and I'm on the PSK Reporter website, and you can see I've got it set up to show all the messages I'm decoding. That's the best one, I think. Asiatic Russia. Yeah, so that's a good old way away, but yeah, plenty of stations across Europe. And you'll see, I mean, look at that waterfall. I mean, of course there's some drift, and that's evidenced if you look at the right-hand column. You can see that same G0 signal. I'm decoding it, but there's a little bit of drift. I've got it at 1790, then I've got it at 1788, and in a minute you'll see it's 1787. But that's only 3 hertz. I mean, that's quite incredible, really. And, you know, would you use it to decode FT8? No, of course you wouldn't if you wanted to do FT8. There's far simpler ways to do it. Even if you wanted to take an analogue route, you know, you'd use a crystal oscillator or something. But I just do it just to make the point about, you know, how stable this thing actually is, that it will even decode it. Now, I'd let the PTO run for a little while so it was warmed up and it settled down. And it does settle down remarkably well. But you can see from the PSK Reporter map down the bottom there that, you know, I am decoding FT8, and it's really quite remarkable that you can get that level of frequency stability with a variable inductor built on a glue stick. So, and it just kind of makes you realise that, you know, if you can do this, then really SSB shouldn't be too much trouble. But yeah, there it is. Who would have ever thought? You know, glue sticks, is there nothing they can't do? Well, thank you very much. I will show you some of the stuff when I finish doing this stuff. If you're interested in any of the things I've talked about, please do go and check out my YouTube channel. And if you like it, you know, please subscribe, and you can keep up to date with all my different home brewing adventures. Thank you very much, and yeah, if anybody's got any questions, I'll be happy to take them. Let me just stop me.
Well, that was entertaining. I enjoyed that. Evening to John, who's joined us, CDL. But I'll open up the floor. If anyone's got any questions, please direct them straight to Nick.
Yeah, Nick. I know you ended up with the audio duplexer. Prior to that, did you try screening at all? And did that have any effect?
I didn't. Part of the reason I thought that is that the commercial one that I bought was screened, and you know, that was 6-7 dB worse than my unscreened one. So I figured it wasn't that. I'm just trying to work out how to stop my. It's all right. I'm just looking if I need to show my. Hang on. Just bear with me one little moment. If I take the portrait off, it means I can show things. Sorry. Yeah. Okay. Yes. So I did. I did. I figured it kind of wasn't that. The screening was really important, obviously, when it came to the actual oscillator, but for the actual mixer, no. I think it just comes back to this double balance mixers. Diode ring mixers really want to see 50 ohms termination on particularly on the IF port, and I've always known that when I build transceivers, when I'm building it for like going into an IF section, I'd build an RF diplexer sometimes to make sure that it's going to see 50 ohms. But I kind of never thought about it with a product detector mixing. I kind of thought, well, it's mixing down to audio, is it really going to care? Well, turns out, yeah, it does.
Now, I have a question from Richard over there in France, who's listening in, but he doesn't want to speak because he's full of cough and cold. Nick, what was the frequency range attained on the oscillator?
I think it was, well, the tweaked version wasn't it something like 6.97 to it was north of 7. It was about 7,300 or something, wasn't it? But it's wide enough. Yeah. So now, depending on what band you were going to construct it for, you would have to see. So I because I was only ever really building this for 40 meters, I didn't experiment too much with trying to enlarge the frequency band that you've got. I mean, I guess what you could do is you could have some mechanism where you could kind of switch in or out capacitance, because that's the other part of the picture. There's not a lot you could do, because I mean, when you've got that, you're probably going to come up against the limits of what you'll do with that, but you might be able to do more with switching in and out some capacitors if you need. I mean, I was just thinking, if trying to do something for 10 meters, it could be interesting, but for some of the smaller bands, then it's pretty big. In fact, the problem I had, really, I was trying to not keep it too too wide, actually. But I confess I didn't really investigate how to enlarge the frequency scope too much.
Yeah, so Richard just said he was thinking about making one for 80 meters. I think that's where the question
Well,
is.
80 meters, you'll be fine, because that's not a huge band. So I would imagine you wouldn't have any problems with 80 meters. I mean, and depending on, because the first one I made, which I think was this one, this has got a truckload of inductor, too much really. So that's why when I ended up with the one I settled for, it's actually a much smaller kind of coil really in the end. But like a lot of these things, there's a lot of experimentation that goes on really. You've got to kind of think it, trim it, and the rest of it.
Yeah, well, I've seen Morse keys made with paper clips and pins, and now I've seen glue sticks used. So I'm wondering who's going to come up with the next stationary item to be used in an amateur radio context.
Wow, yeah.
But no, I do like this. I like the style, Nick. I do like this, building it in these discrete sections.
Yeah, I think the appealing thing, if I can take this one up. Okay, so I don't know if you can see this. You might have to make it big on your screen, but so I'll try and wind it up. The appealing thing is, of course, is you turn this. Now, as you were probably hearing when I was tuning, there's a fair bit of movement here. I could also do with a reduction drive, but I mean, I think when they built these things, they weren't really having frequency stability in mind, really. So you got to hand it to them. It's not really their fault, but. And I have experimented with ways that you can, and some of them are tighter you could do with something that's a little bit tighter, that's not going to move, because you could tune it, but when you take your fingers off it, it moves fractionally, and you know the tuning can be tight. But you can see what I'm doing here as I move this up. You can see that collar coming up, and eventually it'll pop right off the end. So I won't do that. But it has the advantage, of course. You know, if you were to fit one of these in a chassis or something, you haven't got the farhand problem with the thing coming right out and back, you know, because it just all the movement is inside the shaft, not actually on the thing itself. So yeah.
You got any other comments, folks?
I recognised B4BGX. Derek is one of our Lafarge members down on the south coast on one of your last reception on your reception. I actually got brought up on David Gibson books, radio books, going back when I was in my early teens, and he had a lot of very interesting radios, PRS and different ones, and he used to use a lot of used to build a homemade variometer, which has a very similar idea for choosing the local oscillator, and he used to tune them for both ends. He had two variometers, one fine and one coarse, one to go in between bands.
Yeah, right.
And which worked out quite nicely as well. So, but I've still got the David Gibson book. Haven't looked at it for many years, but it was you know that was all discrete components, so using transistors that you probably can't even get now.
Yeah. No, thank you. Yeah. I mean, I think you're right, and I mean the permeability tuned oscillator has been around for a long time, but it kind of fell out of fashion a bit. I don't know why. But I was just surprised, really, the difference it makes when you have fixed capacitance and a variable inductance, even as something that's, you know, as loose as this, you know. The frequency stability is so much greater than even my best attempts to build, you know, like a Colpitts with a variable capacity. You know, it drifts all over the shop, really, and people go to great lengths, don't they, you know, hermetically sealed boxes and things to try and temperature compensation, all this stuff to try and get the thing not to drift. So the idea that you could just fix the capacitance and use a glue stick seems ridiculous, really, but it's pretty good.
A Pierce oscillator is one of the most resilient to actually, if you want something that's not influenced by your hands and changing the geometries or box that you put it in.
Yeah.
You build it and then you box it and then it comes out with a different frequency.
Well, the other one is I've forgotten the name of it now. I've just built one as well, and it's because Charlie Morris did a series. He's not been active again. He kind of pops up from time to time, and a ZL2 CTM. And he came back and he did a series on building. Well, he was actually building an AM broadcast receiver, and which was really interesting because I picked up a few things like his infinite impedance detector and things like that, you know, which was interesting. So I had to play around with some of that stuff. And he got, I've forgotten the name of the blooming oscillator now. Anyway, I built one, which is going to feature in. I'm currently doing a series actually about building. Would you believe, yet another direct conversion receiver? But this one is featuring this particular oscillator, which is really very stable. But it is variable capacitance tuned, but a lot better than other things I've built before.
Being a bit of a valve man as well, and having a plethora of EF80 valves, you can actually use an EF80 if you bias it correctly without putting any HPs on it, just low voltages, and actually use it as a variable capacitor. Actually got valves in the bias voltage on an EF80. That's very, very stable. But you know, it's just that I'm a bit of a valve man and love playing with. But not many people think of using a valve as a variable capacitor, but you can.
Well, that's what it's about, isn't it? It's about ingenious stuff. Yeah, thanks.
Yeah. Anyway, thank you very much for the talk. Very, very interesting, and not too demanding on the brain cells. Fortunately, on a Friday evening.
Good. Thank you very much. You're welcome. Thank you.
Yeah. Is there anyone else like to say anything? But well, they're all quiet.
Comments I'd make. It goes back to something the Germans came across in about late 1944 with some of their low VHF aircraft equipment, which had previously used PTO tuned oscillators with beautifully elegant ceramic silver plated etched spirals on it. And after the RAF rearranged the factories, they couldn't make the ceramic bits and pieces anymore. And they were quite badly rearranged. And they started using nylon, which of course is very, very close to what you're using, which is presumably polythene, I think, I guess.
Yeah.
They found nylon at the time was actually pretty good. And they produced a very similar, I think it was for a superhet, but they actually got a PTO oscillator working with a nylon peg and something very, very similar to that. But only because they couldn't produce a very elegant, very stable ceramic tube with an etched silver thing on it. But they got by with something late 44 and early 45 because of necessity, but got something very similar to that back in those days, obviously with a valve oscillator. But what you've done with a FET is actually pretty much what they were doing in 44, 45, really.
Yeah. No, thank you. That's interesting.
They also used something that I don't know how they got the idea, but they had a round cylinder with lots of holes in it, and they actually had pencils. They used to slide pencils in and out to actually change the frequency. I'm talking about now as low SHF frequencies now, actually, and like half an inch of pencil, was about 300 megs. It was
brilliant.
And of course, you could put different pencil lead types in as well to actually get finer and coarser. But some of the but all that computation has gone out the window now.
That's great, isn't it? Well, you're back to your stationery again, then.
Yeah, see?
You use your pen pot now.
I think the other thing is that there were some very, very, very high-end Collins radios with thermally stable PTO boxes using a highly precision PTFE Teflon rod, which achieve probably not quite the stability you've got with the glue stick. So it's quite good.
Yeah, I have to say it was a real pig to tune it into FDA. That did take some doing, but once it was on frequency, it was amazing, really. But
yeah, so Richard just chipped in again on the messages, was saying that thanks for the talk, Nick. And he said this is a viable alternative to the 2 crystal VXO to replace the crystals. So I can see that. So unless there are any other questions, I think formally I'd just sort of, the chairman's not here, thank Nick for taking the time to join us again this time round. And it's been 3 years, so it's been nice to see you again.
It's nice to be back with you, chaps. Nice to see you.
I say there's not a huge amount of us on tonight, but it will get round again on Zoom and on YouTube. I'll get it right in the end. And I'll catch up with it there, I'm sure. So thank you very much. And we can't really do a round of applause, but thank you.
That's fine. You're very welcome. Good to see you, chaps.